Alrighty, so this is just for the review for algorithms, so hopefully you're not in the wrong place. But as from my understanding, Professor Zachary, he left off on this question in the review yesterday. So we're just going to pick up here, and then I have another exam that we're going to look at after that. So if you ever have any questions, feel free to ask any of them. And if you want to focus on a specific area, we can definitely do that as well. So pretty much this problem here is a dynamic programming problem, right? And the idea of the problem is, so if you have an example like this one called black and blue, can you break up the string into smaller substrings such that each substring is a valid word in the dictionary, right? So you guys did a problem very similar to like this in your homework, but this one is slightly different, All right, so here are the base cases. If your string is empty, you're going to return true, which makes sense, right? Because if we were able to take out a bunch of substrings and there's nothing left over, then we were able to find all these different substrings in the dictionary. Okay, and then otherwise, if the word cannot be comprised of smaller words, then we're going to return false, right? Okay, so the first question is just kind of making sure whether you understand the question. And it's saying give a word where the algorithm should return false, and you can get away by using just about any plural form of any word, right? So if you just pick, algorithms, for example, that would work. All right. So now the first thing you have to be careful of is, so note that he uses base 1 indexing instead of base 0, and the reason he does that is it makes the problem a little easier, but just be aware of that. Be careful when you read the instructions. Right, and then you have your dictionary here where it will just pretty much return true or false if something exists in the problem. Right? Cool. So now we're going to get into the nitty-gritty and just figure out what the recursive relation is. And so you have to figure out, are we taking words off from the front or the back of the word? Okay? So that's the first thing you have to figure out. In your homework, I believe you were taking words off the front, right? And you're slowly making the entire string smaller. In this case, it's going to be the opposite here, right? So the first thing you should note is this or with some bound. And so the idea is, if you're starting to look at the string at index I, right? So like the first time you call the method, I will be equal to n, right? Because you're going to look at the entire string, right? So I is kind of like your upper bound of where you're looking. And so notice how j is going to iterate starting at 0, right? Because you start at the beginning of the string, and then you're going to iterate up until the I. So that's in the very first case, you're going to go from 0 to n, and as we make our string smaller, right, we're going to cut things off from the back this time. So the first thing we're going to cut off is something from the back. We're going to check it if it exists in the dictionary, and then we're going to recursively call the algorithm on the smaller substring, right? So I can't write on this, unfortunately. But so the idea is, so W here, this is our recursive call, right? So this should be at index j. Does that make sense? Right, so you're going to start from 0, and you're going to slowly build up the substring you want to recursively call. Right, so the first time it will be 0, and then 1, 2, 3, 4, 5. Right, so you're slowly building that up. So like in an example, back up to the top. So the first time we call the method on this word black and blue, W of this blank here, which should be j, first time we're going to recursively call it on just the letter B, right? And then we're going to check if the rest of the string exists in the dictionary, right? And so how would you write the rest of the string? Well, that's just wherever you left off, plus 1. So in this case, this will be j plus 1, and the closing index is I, right? That's the very end of the string, if that makes sense. All right, so the first time you iterate through it, you'll recursively call it on B, and then your dictionary will look for the rest, and that's obviously not in the dictionary, so it's going to return false, right? That's why we have an OR statement here, right? Because we only want one case where it returns true. And so like the second iteration, it'll do BL as the recursive call, and then it'll try and find the rest of the string. That one will also return false, right? So we're going to keep repeating this process, and it'll look different once we do the first case where the left-hand side is going to be black and, right? That'll be your recursive call, and the right-hand side will be blue, right? Because blue will return true in the dictionary here, and then here W of I would be, what was that, 7? So you'll recursively call this with that value of 7. Okay. Now the only tricky part is, what is this base case here? So W of 0 means that the string is empty, right? Because you're starting and ending at the very first index, right? And if you look in the example, or in the instructions, it says to return true there, right? Okay, so blank 1 should be true because that's our base case. Second blank is our recursive call. And remember, we're bringing the ending index in, right? We're taking our ending index, which is n at the very beginning, and we're slowly bringing it to 0, right? Because we want to get to our base case. And then the dictionary, this is just checking if the second substring is a valid word, right? So that's going to be j plus 1 to I. Okay, so is there any questions on that one? That's probably going to be one of the harder questions that you're going to have to do on the midterm. The idea is that you figure out what the algorithm is doing first, and then just how to rearrange the different variables such that you're doing you're figuring out what the algorithm is. Okay. Cool. Okay. So now this was the midterm. This was the final from last semester in the fall, and I've blacked out all the answers so we can figure them out together. But if you want the answers afterwards, just let me know, and I can give them to you. But so right off the bat, we're going to talk about the master theorem. And hopefully, that was a little while ago, but hopefully you remember what the master theorem was. But the idea is that you can find some upper bound based on a recursive relation, right? And so the idea you really want to find is A, which is, well, you want A, B, and D, right? That's going to be the important key factors in each one of these questions, right? So B is how much you're reducing your problem by, whether it be a half, a quarter, an eighth. And then A is the number of times you call that recursion. And then D is the exponent of how much work you're doing at each level, right? So like in this example, A is 3, B is 2, and then D is also 2, right? So then if we go back, if we look at the master theorem right here, log base B of A, that's a little more than 1, right? So that's somewhere in between 1 and 2 because it's log base 2 of 3. And then in this case, D is 2, so D is it has a larger influence on the algorithm, so the overall complexity will be O of n squared, right? Cool. Okay, now we go to the next one. A is 2, B is 4, and D is 0.5. And so that's log base B of 2, so that's the same as 4 to the 1/2 power, right? So log base B of A is 1/2. So 0.51, that's just a little bigger than a half, so complexity will be n to the 0.51 power. All right, so this one's a little less clear, right? So the log base B of A, that's going to be like a little over 2. And then 2 to the n, that's much, much bigger than any polynomial expression, right? So the complexity should be O of 2 to the n, right? Okay, so now you have this one where you have log base, same idea here. So log base B of A, this is a little more than 1. So be careful there, right? Because if log base B of A, if you wanted that to be 2, then A would have to be 9, right? So you're not just dividing it, right? You have to do the logarithm. So this term is much, much smaller than n squared log n. So your complexity will be n to the power of log base 3 of 6. Does that make sense? So be careful. You're not always going to just be dividing the coefficient. You actually should never divide the coefficients. Cool. Any questions on those ones? I mean, those ones should be reviewed for you all, but just be careful. Be precise. Okay, and then the next question is talking about RSA. So we had one unit on this where we were talking about RSA. And just remember that to solve RSA, first you're going to have 2 large prime numbers, and then you're going to find your modulus, right? So the modulus is the product of your 2 prime numbers. So in this case, that's 77. And then, so what is the exponent, right? So the exponent is the first number that is co-prime with phi. And if you remember what phi was, that is p minus 1 times q minus 1. Right, so in this example, that would be 60. All right, so what's the first number that's co-prime with 60? 5. Oh, it's 7, excuse me, yes, 7. Sorry about that. But yeah, so that one would be 7. Cool. Now we have to find D. So D is E inverse with respect to phi. Right? So if phi is 60 and E is 7, ooh, that's tough. That's tough. So okay, you have to brute force that. So what I recommend is just doing a lot of you just got to do it on paper. And one thing to note is it could be easier to find the negative modulus, right? So instead of looking between numbers between 1 and 59, it could be easier to find numbers from negative 30 to 30, if that makes sense, right? So this, so let's see if I can do this in my head. No, I can't do that in my head. But let's see. I have a calculator right here on my phone. Let's see. So that one would be. So we had E was 7. The exponent would be negative 1. And mod was 60. So, oh, that's brutal. That answer would be 43. For your guys' exam, I don't think you'll have to worry about it being that complex, right? Because that one's kind of really hard to do by hand. I believe you do get a calculator on this exam, so be sure to bring one. So I think that one would have been easier to solve if you figured out that the exponent was negative 17 rather than 43. But so you just gotta play around with those numbers, yeah.
Are there any band calculators?
Yeah, I thought he said that too, and he was like, your numbers will be easier because
Okay.
you won't get a calculator.
Oh, okay. If you said that, then it'll be much easier. But like, so like, an example of like finding the modulus, the inverse. So like, if I could come up with one off the top of my head, like, if you have, let's say, 62 and 5, right? So what's the modulus inverse of 5 given 62, right? So ideally, what you're going to be looking for is a multiple of 62 where the ones digit is a 4 or a 9, right? Because that way you can always find a term that has a 1 digit with a 5 or a 0, right? So the idea is so what times 62 will give you something, a 4 in the ones digit. So first thing you'd want to try is 2, right? So 62 times 2, that's 124. And then 125, that's 25 times 5. So the inverse would be 25, right? Does that make sense? How you do that? Okay. Cool. So just make sure you're comfortable with that. Okay, so now we're getting into another recurrence relation problem here. And so the idea of this one is you have a linked list and you're trying to find, I believe, the size of the list. But ideally, you're just trying to come up with a recurrence relation to eventually find the complexity of the problem. All right, so the first thing right off the bat is you find the size. For a linked list, that's a constant operation, so that's probably not going to be too important. This is your base case here. It's a constant complexity. So right here, you should immediately be able to tell T of 1 is O of 1, right, is constant, because all we do is return 0. Now, the other case is the recursive case, right? And so you have to kind of figure out what we're doing here. And so if you see that we have this while loop, and inside the loop, we're always taking off the first element. And then we break out of the while loop once our size, the size of the list is now a third of the original size of the list, right? So we're removing 2/3 of the elements. All right, and then we're going to recursively call the same process with the list that's 1/3 the original size, right? So T of n, we're only call it once, right? So A will be 1, so it should be 1 times T of n over 3, right? Because we divided the original size of the list by 1/3. And then for each, so what was the amount of work we did at each step, right? We had a constant operation here, and then we removed 2/3 of the elements, right? So that is O of n. So eventually your recurrence relationship should be T of n equals T of n over 3 plus O of n. Does that make sense? Right? Because For each one, we only recursively called it once, decreased our problem size by 66%, so we divided it by 3, and then this removal is a linear cost. Okay, so now we're going to get into some true-false questions. Oh, I forgot to black that part out. Well, that's okay. There we go. So this one is, the first question is, so does every DAG have one topological ordering? So is that true or false? False, right? Because you could have conditions where maybe two elements could be swapped in the topological ordering. Cool. Nice, you guys got that one right. So this one, okay, this problem here, a lot of people got wrong last semester. And it's pretty much asking is, can Dijkstras' algorithm terminate if you have negative edges in the graph? Right? So first thing you should note right off the bat is that even if it does terminate, the algorithm is not guaranteed to give you the correct answer, right? Because Dijkstras' algorithm only works with positive edges. But does the algorithm terminate? And it should be yes, right? Because you're going to look at every edge and every vertice only once, right? And the way you go about it is it has a higher complexity, but you're only ever going to look at every edge and every vertex once. Cool. So that one should be false, because it will always terminate. Cool. All right. So now if you were given a graph, so Prim's and Kruskall's algorithm, would they return the same thing? Do they always return the same thing? Right? So Prim's and Kruskall's, that's a minimum spanning tree problem. Right? So the idea behind Prim's is it's a greedy algorithm, right? Where you're always grabbing the cheapest edge that leads to a node that hasn't been visited yet. And Kruskall's algorithm is a disjoint set problem, right? Where each node starts as its own disjoint set, and you eventually merge all the sets together, right? So they both do the same thing, but so since they have different strategies of going about the algorithm, it is possible for them to have a different minimum spanning tree, right? Like an example of this would be if you have a densely connected graph where every node points to every other node, and the weights of each edge are all the same, right? So there could be multiple variations of how you connect the edges, and no matter how you connect the edges, they'll all have the same cost, right? So it's not always guaranteed to give you the same tree, but the cost of the trees will always be the same, right? And then, quick question, which one is faster, Prim's algorithm or Kruskall's algorithm? You guys remember? Nope, it was Kruskall's algorithm, right? Remember it had that E plus V log star V algorithm, right? Because it had that path compression in the disjoint sets, so that will be just a little bit faster.
What was Prim's complexity?
I believe that one was E plus V. Yeah, because you look at every edge and every vertex once. Yeah, both are really fast though. Okay, so now we're going to get into some P versus NP, so this should be pretty fresh. We talked about this last 2 weeks. But I mean, these problems definitely can be kind of tricky. So this one is talking about an approximation algorithm for the traveling salesman problem, right? So we talked about that briefly. And it's saying it has this complexity here, where V is the number of vertices and C is some constant. All right, so this is suggesting that they have a polynomial solution for a approximation algorithm for traveling salesman. And so pretty much the question is asking, if we have this polynomial solution to the traveling salesman problem, what does this suggest about P versus NP? All right, so are they the same, or are they different, or does the information provided yield no solution? All right, so you gotta be really careful here. And the real giveaway is that they used an approximation algorithm. Right, so they're not actually solving the traveling salesman problem. So that's great that they have a really good approximation, but that doesn't tell you anything about P versus NP, right? Because they're not actually solving the traveling salesman problem. So be careful. Make sure to really focus on the wording of these problems. Okay, so this next one is talking about reduction. Okay, so the idea is that they're trying to determine if factoring a number is an NP complete problem. And so you have a bunch of it's a multiple choice question, and then you have, which one of these multiple choice answers would guarantee that the factoring the problem is NP complete, right? So the first one is you have a reduction from factoring into the 3-SAT problem. And just so you know, the 3-SAT problem is an NP-complete problem. I'm pretty sure we talked about that in class, but that's just so that's important to know for this problem. And then you have a reduction from 3-SAT into factoring. And then you just find a polynomial time algorithm for factoring, find an exponential time for factoring. Right? So right off the bat, you know 3 and 4 aren't really important, because if you find a polynomial time for factoring, that just means the algorithm is an element of P, right? It doesn't really tell you anything about it being NP complete, right? And then you can say the same thing about question 4. So question 4, if you have an exponential time for an algorithm, that doesn't actually tell you if it's in P or NP, right? Because if to be an NP, that means your solution has to be verifiable in polynomial time. So really 4 doesn't tell you anything at all. So that solution is completely useless. All right, so that brings it down to the reduction, right? And if you want to show something is NP complete, you show that a known NP complete problem can be reduced into the problem you're trying to show is NP complete, right? So 3-SAT is our known NP complete, and so we want to show that reduced down into the factoring problem. So question 2 is your solution here, right? So you already know this has to be true, because 3-SAT problem is a known NP complete problem, and by definition, every NP problem can be reduced into an NP complete problem. So this doesn't tell you anything new. So that should be another giveaway that 2 is the right answer. Okay. Oh, that didn't work too well. So this one, the idea is that if you're given a graph with negative edges, and so pretty much assume W is just is a positive value, right? And so the negative edge is negative W. And if you add W to all the edges, so you have a bunch of negative edges, assume negative W is like the most expensive negative edge. So like that would be a graph, say, like you have A, B, and C. A points to B with negative 5, B points to C with negative 2, and A points to C with positive 3. Right? So you want to run Dijkstras' algorithm on this graph. Can you just add a constant cost to each edge such that all the edges are now positive weights? Right? So can I add, say, 10 to the cost of each weight such that now all the edges are positive, and I'll be able to run Dijkstras' algorithm? Right? So is that a valid operation to make sure Dijkstras' algorithm will work? And we actually did this example in class a long, long time ago. And right, so this is not valid, right? Because you're messing up the ratios between the weights, right? So so like an example of this of how this would not be correct. Let's see. Oh, is there a pen? Yeah, that'd be perfect. I'll draw an example on the board here. Okay, so like an example here would be, say like we have a graph like this. We have a negative 3, negative 3, negative 3, and then 5, right?
All of the 5?
Actually, let's make it 0. No, let's make this one negative. So how do I want to run this? Yeah. Is it -2? Okay, I think this one will work. Okay, cool. So the idea is that this should be the cheapest path, right? Right here. So if I add 20 to each edge, just for an example, so I take that out, this is 17, 17, 17, and then this one becomes 18, right? Now, since I've added a constant amount to each edge is positive, but now the algorithm will think this one is the shortest path, right? And that's not correct. So this is just an example of a case where this does not hold true.
Could that be enough to
right, for this instead of because he wrote a whole.
Yeah. So he wrote an example like in the solution just so people would understand. But you could just give an example of a graph like this, and it would suffice.
Can we just draw it? Yeah.
Yeah, definitely. For this problem, the explanation is just to help people like going back on it to understand the problem. Yeah. So you can definitely draw it if you want. Okay. So this one is talking about Radix Sort. So if you remember what Radix Sort, it was an in-place linear scan algorithm, right? So we were sorting each number based on its digit, right? So first time we would sort based on the ones digit, and then the twos digit, and the third digit, or you could do vice versa, or you could sort based on 2 digits at a time. There's a lot of different variations of it, but the idea is that you're slowly going to replace. Well, you're slowly going to sort the algorithm based on a single number, right? And that's why it can be so fast. It's because you don't actually compare the values to each other. Okay, so that's just really brief recap on Radix Sort. And so the algorithm is saying, so instead of using the counting sort, so that was where we were looking at each digit and figuring out where it should go in the final array, right? Instead of looking at using a counting sort, could we use any sorting algorithm at that point to sort the numbers, right? So the idea is that you can use some sorting algorithms, right, at that point. There was just one condition you have to meet, right? And that condition was that however you're sorting the numbers, it's a stable sort, right? Because you're basing the numbers that are already pre-sorted based on like a previous digit, right? So if you mix them up based on like the second digit, you could be messing up the entire sorting algorithm, right? So if you use something, yeah, go ahead.
What's the difference between a stable and in place?
Yeah, so a stable sort would be like if you have, say, like you have two, we'll still call this 2A and 2B, and like say like this was 3 and 1. So these have the same value, right? They're both 2, and in the final sort, 2A will appear before 2B because it occurred earlier in the list of numbers, right? So stable just means if there's a tie, they'll preserve the order they're already in, right? So like that, this could be really bad and say like, let's think about, say like you have like 152, 53, and like 80, right? So first you sort on the first digit, so you'll have 80, 1, 52, 53, right? And now you're gonna sort on the second digit, right? And so you should get our original list back, right? But if it's not a stable sort, since 5 and 5 are both the same value, if it's not guaranteed to be stable, you could get like 53 coming before 52, right? That would be a problem because now now it's not sorted anymore, right? So if you use a stable sort in between, like merge sort, then it will work. But if you use like an unstable sort, like quick sort, it's just not guaranteed to work, right?
I think insertion sort's another stable.
Yeah, that's another example of a stable sort. Yeah, so this one's false. All right, so this one's talking about dynamic programming again, right? So the idea of a top-down approach, right? We're starting with our big problem, and we're going to break it down into smaller problems using recursion, and then we're going to build it back up using the solutions to the smaller problems, right? So that's the whole concept of dynamic programming, right? So the larger subproblems are solved before the smaller ones, so this should be false, right? I mean, we start with a bigger problem, but we're going to break it down into smaller ones, solve those ones, and using the smaller solutions, we're going to figure out the answer to the big one. Okay, cool. That one's false. So this one, now we're talking about the knapsack problem. And so if you remember the knapsack problem, that's like if you have a bunch of objects of different weight and different cost, and you have a limited amount you can carry, what's the maximum cost you can bring with you, right? Okay, so now you're saying, can you solve the knapsack problem where you have an object I with the greatest value to cost ratio, right? So this should be telling you they're trying to do a greedy solution here, right? They're trying to pick as many elements that has the best weight to cost ratio, right?
We did this in class.
Yeah, we did this. We might have done this exact problem in class. I don't remember. But since it's greedy, right, you should know, oh, well, the knapsack problem is not, it doesn't have optimal substructure, right? So you can't just break it down and solve the smaller problem and do the same greedy solution for every single one. So that one won't. That's not true, right? Because that one cannot be solved using a greedy solution. So that one should be false.
What's the clue in that sentence that tells you that you're looking?
Yeah, so right here, you see how they say they will always pick the object with the greatest value to cost ratio, right? So they're doing the same action over and over and over again, right? They're not trying different possibilities. They're always just trying to pick one object, right? So that's their greedy choice, right? They're always trying to pick something with, in this case, it has the best weight to cost ratio, right? Or cost to weight ratio. Okay. Cool. Yep. Cool. So now this one's asking, does Dijkstra's shortest path algorithm run in O of v cubed for a graph with v vertices? So be very careful here on what does big O stand for.
Upper bound.
Right, it's an upper bound.
So sure.
Yeah, so this one should be true. So be very careful. But remember what if they ask for a tight upper bound, then this would be false. But notice how they didn't ask for a tight upper
Dijkstras
bound.
was v plus e log v, right?
Yeah. So yeah, the complexity of Dijkstra's is e plus v quantity times log v. Right? That log v was coming from the heap that we were using to process the nodes. So be careful. That one's very tricky. Wow, that didn't. Well, that's unfortunate. All right, so this one you're just comparing values, right? If it's big O, big theta, big omega. Sorry about that. But so the first one is saying if you know something is exactly n squared, is n log n, is that going to be an upper bound, a lower bound, right? So this should be a lower bound. So f is an upper bound on g, right? So that's how you get that O of f. So then you have n log squared n, so that's a lower bound here, and you have an upper bound on g. And since f is larger than g, right? So f will always be an upper bound to g. Cool. So this one is saying if a program could run in at least n, complexity n, and then the second algorithm is going at most n squared, right? So you could have this weird case where, like, you could have where this algorithm f is in, say it's exponential, and this one's n squared, in which case f would be bigger, or you could have f run in linear time, in which case f would be smaller, right? So you have a contradiction there, so you can't make any conclusion. Okay. And then this one is the same idea here, right? Since these are just upper bounds, right? There doesn't tell you the exact complexity of the problem, right? So one example would be g running in constant time and f running in linear time, or vice versa, right? So you still can't make any conclusion on which one's always going to be faster. Okay. So this next one is talking about radix sort again. So remember, radix sort is it's linear on terms of the number of elements and multiplied by what the radix is, right? How many times you're looking at the radix. In our class, the radix has always been one digit, so we've usually only sorted it by one digit. But anyways, the important thing to remember is that it's linear cost, right? So the idea is, say you have n k-bit integers. So you have n numbers, and it runs in t seconds. So if you were to, say, double the number of elements, what would you expect your runtime to occur? Right? It should double as well, right? Because you have twice as many elements. Since it's running in linear time and the radix is staying the same, then your runtime should double as well. Okay? And yep, that was the first one. And then the second question is saying, well, what if we were sorting, say, numbers where they were twice as large, where they have twice the number of bits? Right, now what's going to happen to your runtime? Is it going to double, quadruple, or stay the same? Right, so in this problem, your radix is doubling. Right, so we have twice as much values to look at for each number. It's going to take twice as long to sort, right? Because we're going to have to go through twice as many bits. So that should be another indicator that the runtime will only double. Right. Okay, are there any questions about that one? That one's not super intuitive.
If you look at 2nk and then n2k, they just switch where the 2 is. It didn't change anything.
Yeah, because it's it's just because each element's going to take twice as long to sort in this example here on the bottom. Okay. All right, so we have linear programming. I'm going to come back to this one and do it at the end because it will take a longer time, and I'm going to need to draw it. So I'll come back to that one. So here we're getting into more RSA stuff, right? So we have a couple operations here. So you have signing a certificate, verifying the authenticity, sending an AES key, and receiving an AES key. I believe we talked about AES keys in this class, but just to review, it's kind of like a one-time it's a one-time key to encrypt and decrypt a message, right? It's like a one-time pad. And so the idea here in RSA is, say like I want to make a transaction online. So whoever I'm making the transaction with, they will send me, like if it's Amazon, they will give me an AES key. And I'm going to need to verify it came from Amazon. And then I'm going to decrypt it using my own private key, right? Because Amazon's going to first encrypt it with my public key, right? Because they only want me to figure out what the AES key is. And then they're going to encrypt it with their their private key, right? It's kind of like to sign off as saying this came from Amazon, right? And so you know that it's coming, whatever the message is, it came from Amazon, right? Because you wouldn't want to use a key that came from a malicious source. Okay. So the first thing right off the bat is we're encrypting it with a public key. Right, so for example, right back to the Amazon case, they encrypted the message with my public key, right? It's because they're trying to send the message to me, right? Okay, and now you're encrypting it with a private key, right? So that's Amazon, they encrypted it with their private key it's kind of like to sign off on the certificate, right? They're trying to show that this came from the Amazon source, okay? So now we're talking about decryption. So if you're trying to decrypt something with a public key, right, that's trying to verify, right? So if I get a message from Amazon, I'm going to try and decrypt the message using Amazon's public key just to make sure I know the message came from the source that claimed to be sending the message. And then decrypting it with a private key, so that's trying to decrypt a message that was meant only for me, right? Someone encrypted it with my public key, and I'll decrypt it with my private key, right? Any questions on that one? So that's just like another high-level overview of what RSA does. Okay. Alright, so this one is another dynamic programming problem. And so we're talking about the knapsack problem without repetition, right? So that's the idea. If you have a limited number of pieces to pick up, once you pick it up, you can't pick it up again. Right, so it's saying pretty much that you don't have infinitely many of every type. Okay. So here they're talking a little bit about what the treasures are. So you have n number of things you can pick up, and each one has a cost, right, associated with it. That's what W of I is. Or V of I is the value, and W of I is how heavy the object is, right? And so here's they give you a recursive definition, right? And so pretty much you're saying, so K of I is maximum value that can be stolen. So this is what you're trying to maximize, right? You're trying to maximize what K is. Okay, and I believe I is the item you chose, and then J is the capacity, right? So if you don't pick any items, you're not going to have any gold, right? So if you don't take anything, you're going to have 0 cost. If you want to pick an item but you can't carry it, right? Then you have zero value as well, right? So those are your base cases. You either run out of space or you run out of things to pick, right? So that's pretty much what the problem is saying here. Okay, so you see how we're trying to maximize it because we're trying to take as much gold as possible. So this is a little intimidating, but so just note that this is a ternary operator, and it's like an inline if statement, right? So pretty much what it's saying is if the weight of I is greater than the amount that I can carry, then I won't pick it up, right? Then it has 0 value to me. Otherwise, I'm going to take its value, which is V of I, and add it to the recursive problem, right? I'm going to decrease my load and decrease the number of elements I can pick up, right? So pretty much all it's saying is if I can carry it, if I can't carry it, it has zero value to me. If I can carry it, I'm going to add the value and then recursively figure out what the next item is. Okay, and then this is the idea where you don't pick any element right off the bat. Okay, so that's just saying the number of elements you can look at decreases by 1, and then the amount you can carry stays the same, right? Because you didn't pick that element up. Okay. So now we're going to talk about. So I think that's the hardest part with these problems is understanding what's going on. Once you kind of understand what's going on, then the recursion becomes pretty simple, and then memoizing the solution can become pretty simple as well. All right, so we have a bunch of different ways we can go about solving it. We have direct recursion or memoized recursion, right? So that's where we're going to implement a cache and keep track of values as we go. Or we can fill out a table and kind of brute force our way to figuring out what the solution is. All right, so the fastest one should be the memoized one, right? Because we're going to only look at values that are viable, right? And then we're always going to be using our cache, so it's going to be really, really fast, right? And then the direct recursion should be the slowest, right? Because that's just a brute force algorithm where you're going to just recursively call things over and over again. And that should probably be exponential. The memoized recursion, like that, you could probably get that in like maybe n squared or n cubed, depending on the problem. And then systematically filling out the table, you're going to look at a lot of cases where you don't look at those cases in the dynamic approach, or in the memoized recursion approach, right? So it's going to be it's going to be much faster than the direct recursion, but you're going to be looking at a lot more cases compared to the memoized approach, so it's going to be a little slower. Okay. Okay, so this one's talking about a max heap, just drawing the max heap. And you can draw whatever max heap you want as long as it's a valid max heap. So first thing you should note is what is a max heap, right? That's important. So the idea is such that every node every child of every node is smaller than its respective parent, right? And then the second key thing you need to make sure about a heap is that you fill up the heap from left to right, from top to bottom, right? Okay, so I think the easiest way to go about this is just add elements from largest to smallest, right? So you have 17 as your parent, then you might have 11 as the left child, 13 as the right child, and then you'll have 2, 3, 5, 7 on the bottom row in that order.
If you just flip it, it works.
Yeah. So
The right in the other direction.
yeah. So just make sure you understand what heaps are. They're pretty important, right? We talked a lot about them, especially when we talked about Dijkstras algorithm.
Would we have to actually draw
Yeah.
a binary tree, or could we just draw the array and call it a heap? Because technically you just flip it.
Yeah,
as
I believe for this problem the professor wanted you to draw it as a tree, but we're not going to be. We won't be too picky about it. Okay, so I believe this is. Oh no, this is not quite the last. But this one, you're pretty much trying to find a recurrence relation for this problem. Okay, so the problem's not super straightforward, but what they're trying to do is they're trying to multiply two n by n matrices together. And they claim here that there is an algorithm such that if you reduce the matrix by half, and then you do this 7 times, right? So you have 7 pairs of n over 2, and then you add a few matrices together, then you will you'll come up with a faster solution, right? And so the idea is, so what is A, B, and D? All right, so A is 7, right? Because we're going to do this 7 times. B is 2, right? Because we're having the problem every time. And D, so this one's not quite as clear, but notice how they say at every level they're going to add a few matrices together, and the cost of adding matrices together is n squared, right? So D should be 2. Cool. And then based on that, so you have A, B, so you have 7, 2, and 2. So log base 2 of 7, that's almost 3, so that's a really high value of 2 point something. And then D is 2, right? So in this case, D is smaller, so the complexity should be n squared. Or, sorry, n, this would be n to the log base B of A, because that one's larger. So it'd be n to the log base 2 of 7. So almost a cubic algorithm. Any questions on that one? So if you haven't noticed the trend, all the hardest problems have to deal with interpreting the problem from like a paragraph or from a bunch of symbols. So make sure you're really good at that, right? Being able to understand the problem is, if not the most important part to finding a solution, right? Okay, so now we're gonna have some quick free response questions. So this one is talking about, you have an undirected weighted graph. So notice it didn't say anything about the weights, so they could be negative, right? So two vertices are chosen at random, and you're trying to find a path from U to V where the total is less than or equal to D, right? So we're trying to see, can we get to this location with a cost D, right? So prove that the shortest path problem is a member of NP. So how do we do that? How do you prove something is NP? Right, you just have to show that given a solution, you can verify it in polynomial time, right? And we can easily take a path and just verify if it's correct in polynomial time, right? We're going to check if our starting point and our ending point are U and V respectively, and that we have that each path is continuous, right? And then we're going to add up the cost of all the paths and make sure that it is less than or equal to D, right? Whatever our cost was. Okay? So you just have to make sure you can verify it in polynomial time. Okay, so this one, this is a heavy hitters problem. All right, so you have all these numbers, and so a heavy hitter just means that the number occurs, I think, more than half the time, right? Right here. So it occurs more than half the time, and then you're trying to find an efficient algorithm that finds all the heavy hitters in the graph, right? So first off, you should note, if there is a heavy hitter, it should only occur one time, right? And now you have to find, so when he says efficient here, he made an edit to this. He wants you to find a linear cost algorithm for this problem, right? So note that all the values are integers, right? So that should tell you right off the bat you might need to use like a radix sort to make it really, really fast in linear time. And right, so even if we do have it in, we sorted order, if we sort it in radix time, so we're already at complexity of linear cost, how will we find what the maximum value is? Right, so we know each number is going to be sorted, so first time we see a number, we can start a counter, right, and count how many times it appears as we go throughout the sorted array. And once we find a new value, we're going to look at our count, and did our count occur more than half the total of the elements? If not, then we're going to try counting again, and then if not, we're going to keep doing this process over and over until we get to the very end of the array, right? And in which case, if we get to the very end and there weren't any heavy hitters, we're going to return 0. Otherwise, if we do find a heavy hitter, we'll just return that, and then we'll be able to break out of our algorithm early, right? Because there can never only be one heavy hitter, right? Okay, any questions on that? That was midterm from last year. We went through it kind of quick. You guys didn't have too many questions, so you're probably pretty ready for the exam. But any questions right off the bat? Anything? Yeah.
Is this going to be available online?
Yeah, I can post it if you'd like. I'll take all the black, I'll put all the answers back in. Yeah. Okay, so now we'll go back to that linear programming one, because this one takes a longer time. And I believe you're supposed to bring a ruler, right? Did the professor say to bring a ruler? All right, well, maybe you might not have a linear programming problem then, but don't count on it. All right, so this one, so you have a bunch of types of dog food, right? And so now how do you make up each item of dog food, right? So we're gonna have F and T, right? F and H are two types of dog food. All right, and so we have a bunch of constraints for each type of dog food, right? We have cereal and meat. Okay, so we have dog food F requires 1 pound of cereal and half a pound of meat, and sells for $7. right? Okay. And then we have a dog food H, which uses 2 pounds of cereal and 1 pound of meat and sells for $6. Right? So the $6 and $7 is probably going to relate to our optimization statement, and then these quantities of meat and cereal are going to be constraints, right? Right, and then you have a cost for cereal and a cost for meat, right? And then we have a packaging cost as well, right? Okay, and then here's going to be some of our constraints, which we have a certain amount of weight in cereal, a certain amount of weight in meat, and then the production bottleneck is that they have a certain number of bags, right? So they're only going to make so much. And then they're going to try and maximize profits, right? So first thing is, let's try and create a constraint for the amount of cereal, right? So we have 240,000, right? And so the number, that's pounds, and so we have 1.5 for F. And then for H, we have 2 pounds, right? Right, so that should be one constraint right off the bat, right? So this is the constraint based on cereal. Right, so now we're also going to have a meat constraint. So this one is going to be 180 grand. All right, so then this one should be, I made a small error there. So that should be 1 pound of cereal for F and 2 pounds of cereal for H. Okay, and then for meat, the first one had 1.5 for F. And then for H, it was 2. It was also 2. No. 1 pound of meat for H. Right, so that's your meat constraint. Now we need to come up with our baggage constraint, right? So that's 110 grand is less than or equal to F plus H, right? So the number of bags that they can use is the number of, that's our third constraint, right? Because they can only make F plus H has, well, should be, these should all be less than or equal to. Right, so this is a packaging constraint. All right, and then we have an optimization constraint, or well, this is our optimization statement, will be cost, right? So for optimization, so for F, we have, it sells for $7, so it'll be 7 minus times F. Right, and so the minus is coming from the cost of food, right? Alrighty, it costs $1.40 to package. So F, so it's gonna be minus 140 for packaging. Okay, and then for meat, costs $2 per pound, and then the amount of meat in F is 1.5, right? So it's the minus 1.5 times 2, and this is meat. And then we're going to be subtracting also the cost from the cereal, right? So I believe this one takes in 1 pound of cereal, and cereal costs, is it $1?
Yeah.
Yeah. So it'd be minus 1 times 1, right? Cool. And then the other one is 6. You get starts for $6, right? And then it has one. Let's see how many pounds of cereal is this one.
2 pounds to $1 for cereal.
Yes. So $1 per pound. Oops.
$1
Yeah, it's $1 per pound, and they have 2 pounds of cereal. Right, so that's minus 2 times 1, and then the meat cost was
2 to 1 as well.
it's 2. Okay, well that works out really nicely. And then you're also going to subtract a $1.40 for packaging, I believe. Or 0.6 for packaging. Right, so this should be your optimization statement on top. Right, and so you'll take that, you'll reduce them, right, and then you're going to get a graph that looks like this, right? So the feasible region, right? So since all of our problems are less than or equal to, you're going to draw all these lines. Like here's an example of the serial constraint. And your feasible region will be everything below the line, right? Because it's less than or equal to. Right? And so you're going to have these points of interest. So like here's one, here's another point of interest, another point of interest, and then another point of interest, right? So here's your serial constraint from the equation we drew. And then you have your meet constraint. And then this is our packaging constraint. So you're going to plug in the values for each one of these into your optimization statement to find out which one is the best one. And then that will be your solution. Okay, is there any questions on that? So these ones, that one's kind of like, you just got to, it's a lot of busy work in my opinion. But yeah.
You got the 0 to 12 points from that optimization constraint, right? 11, 0, 11, 5, 0, 12.
These ones?
Yeah, like any of
Oh, so these are coming. These are intersection points between the bounds, right? So like this is an intersection point between that. There can't be less than 0 values. There can't be 0 bags of H, right? So where the two bounds intersect, you have a point here, right? And then here's another intersection point between different bounds, another intersection point, and another intersection point.
Where do you get the 12 from?
This is just the intersection of the lines. So if you calculate what that intersection point is, it will occur at 0, 12. So like that'd be like saying, what's the intersection of these two lines? If you do the math, you'll get 0 and 12. Yeah. So I think you'll have easier problems though, just because they had a calculator for the last exam, so that's why theirs are a little harder to find out.
It's going to give us one of these because it seems like it would take us a while.
Yeah, I mean, every exam I've seen that they've been on there, but so I would expect one, but I mean, if there isn't one, that's nice, right? I mean, if you don't have one like this, you'll probably have a duality problem instead. That'd be my guess, but I'm not sure.
What's the duality thing again?
So duality is like, so see, you see how we have like a minimization problem here? How can we change the constraints such that it becomes an optimization problem? Right, so that's the idea behind duality. I don't think you'll have one of those though. Those ones can get very ugly very quickly. But yeah, so I mean, especially with a problem like this where you have a lot of bounds and the coefficients aren't easy to work with, then I wouldn't expect you to do a duality problem on this one. But the whole idea behind duality is that sometimes it can be easier to find a minimization point rather than an optimization point. Some algorithms are better at finding minimums. And so you'll like to take an optimization problem, find the dual, and then solve the minimization problem here. Right.
Our flow problem was like this, right? When we graphed out the soda one, you remember?
Yeah, it's very
simple.
simple. Yeah. But yeah, so like the dual would be an example of where all these lines here, instead of being less than, right, they're all going to be greater than. Those will be your constraints there. And then you'll try and minimize the points associated with the dual. But yeah, so that one wraps up this midterm. Now I have a lot of time left over, so I went a lot faster than I anticipated. So I have a couple other midterms if you guys would be, or I think I have another final if you'd be interested in looking at that one.
Can you post that one also?
Yeah. I'll post a zip file with like a ton of materials. Like, yeah. Actually, it might be faster. Let's see if I can go to my old courses. Let's see. This one. Yeah, question? Okay, yeah.
So I can compare.
Okay, this one. So this was from my year, a long time ago. Okay, so this was my final exam when I took the class. So we can go through it. So, like right off the bat again, we're going to have a lot of similar master theorem. There's definitely going to be at least one question like this one, right? I think the only really interesting one out of these, like this one is definitely interesting here, right? Because you have this n squared log n. So how do what value do I treat that for d? Right, so just treat d as some like 2.00000001, right? It's just that log adds a very, very small value to the polynomial. But any set polynomial will have a greater complexity than an n squared log n, right? 2 to point anything will always be greater than n squared log n.
If it's n log n, it's like 1.03001.
Yeah, yeah. I mean, really, you can't actually give an actual value because it's exponentially slow, right? It doesn't actually have a exact polynomial value, but you just treat it as it's some really small number, right? So this is like 2 point, I want to say, like 3 log. Oh no, it's probably even more than that. Yeah, no, this is probably 2.3. Log base 2 of 5, that's probably about 2.3. So 2.3 will always be greater than 2.0001, right? So the complexity is n to the log base 2 of 5. So that one could be a little tricky if you're not comfortable with this log term in the d coefficient. So make sure you're comfortable with that one. So this one, log base b of a is smaller than 1, right? So the complexity will be O of n. Right, this one's n log n, right, because they're both the same. And then this one is, so this value is slightly less than 2, right? Log base 4 of 15, that's slightly less than 2. And so the complexity is O of n squared.
Hey, let's just skip to the interesting ones.
They're all interesting.
I know, but I've sensed a theme now. We're going to see the master's theorem, right? We're going to see like the big O stuff. We're going to see RSA. That's an interesting one.
Oh yeah, there's this problem again. Oh, I used the same problem twice.
Exactly. That's what I'm saying. Like,
Alrighty, let's see here.
they're starting to feel really similar. So we should focus on the hard ones.
Alright.
Are these all from Joe, not from another teacher?
This is from a different professor, because I had a different professor when I took the exam. Yeah.
Okay.
Yeah, this is the first time I've TA'd for Professor Zachary. But so this is a really interesting problem. So if you have a metagraph on a DAG, so if we ran the strongly connected components algorithm on the DAG, would it be structurally identical to the original graph? That's a true or false. Right. So what does the strongly connected components algorithm do? Right. Essentially in the metagraph, each cycle is represented as a single node. Right. That's all the strongly connected components algorithm does. And if we have a DAG, there's no cycles. So the strongly connected components algorithm has nothing to do. So the graph will remain the same in structure. Right? So that one's true. Oh, this one, okay. So this one's talking about depth first search, right? So you have pre and post times where you're going from U and V. So U has a pre and post time of 15:18, and V has a pre and post time 11:22. So first off, is that possible, right? If you have a edge from U to V, is that possible? Right. Right, so that should be possible, right? So an example of this is, say, like you have your DAG here. Say you start visiting say you start your depth first search at U here. Right, and so that's maybe give it a 1, it'll do some other stuff, it has a post time of like 5. Right, and then you can start maybe have a value here where it's like 7, it goes down to do some other nodes, and then it comes up, it has a post time of 15. Right, there's still a connection from U to V. Oh, oops. Should be V. This one should be U. But the pre and post time are later than the children's pre and post time, just based on how the depth first search looked at the nodes. Right, so that one should be true. So yeah, we already went over that one. We went over that one. Oh, these ones have a lot of same questions. This one's we definitely didn't do any of these. This is just modular arithmetic, right? So 12 mod 7, that should be really easy. So 7x 13 is equivalent to 13 mod 15. So this is you're doing you're finding the inverse of 7 with respect to 15, right? And then you're going to multiply the inverse on both sides to solve for x, right? So the inverse of 7 is -2, right? Because 7 times -2 is -14 plus 15, that's 1. So -2 so we'll multiply -2 to both sides. So x is equivalent to -26 mod 15, which if you add 30, that's 4, right? That'd be an example of how you do the modular inverse to solve for x, right? And that's almost exactly what you're doing here as well. So what's the inverse of 5 with respect to 8? So that's -3, so that's 5. Right, 5 times 5 is 25, which is 1 more than 24. And then you'll have, so usually if you see a problem like this, the answer is either probably going to be 1 or -1, right? If you see, but now you just have to figure out which one it is, right? And so 2 to an even, 2 is the same as -1 mod 3, right? So -1 to some giant even power will be 1. And so we'll have 1 left over 1. And so so this whole statement is equivalent to -1 mod 3, which is the same as 2. Right? Does that make sense how I did that one? So usually you're really going to want to try and find something such that the base to some power is going to be either 1 or -1, and then you can scale that up to solve the problem here. Okay, this one's really interesting. So how many numbers have a multiplicative inverse with respect to 26? Right? It's just all the numbers that are coprime with 26, right? Right, so this would be, 24 numbers. If you do it really fast in your head. Most people will just write them out though, right?
It's just you take the prime factors of it and then subtract 1 from each and multiply together. Because you just treat that as if it's a...
Okay. So there's more bound problems. I feel like we're pretty good on that one, so I'll skip that one. That one was we already did that one. Let's see. Yes, this is a pretty good one. Number 11. So if you have an algorithm where the complexity is n to the log base a of b, where n is your input size, okay, and so what will the value, how will you change your input such that the complexity increases by a factor of a? Right, so you have some runtime where it's n log base a of b, right? And you want to do something such that, so say this ran in, let's say, t seconds. You want to figure out a new value for n such that the algorithm runs in a of t seconds. Right? Does that make sense? Right. Cool. So we're going to change n such that so we want some term such that n to the log base. So we'll have some constant c, log base a of b. Okay, so we know n to the log base a of b equals t, right? So we want to find some value c, log base b or a of b equals a, right? Okay. This one. Oh, okay. I was gonna say that's really hard to solve, but I misread the problem, so that's my bad. So here, I'll erase it. So what it says is it wants, so say we had n to the log base a of b. So this is t, right? This is the same, but the problem wants to find some n, some input, such that the running time is a times t, right? So this should be a little easier to solve, right? No, sorry, no. That's the way I just did last time. So you change the input to a of t log base a of b. What is this equal to? Right. That's what the problem's asking. Right, so we just split it up. That's a log a of b times the same times this again. So this is the same as b times t. Does that make sense? Okay. Yeah, just be careful with your how you distribute exponents and stuff like that. Okay. So this is an example of a disjoint set problem where this is almost the same as your homework, right? Where we just make a bunch of disjoint sets and we combine them together using the union operator, right? And the only thing I would note on this one is you only change when you combine two sets, right? Because every set has like it's like value, right? It has some degree of the set, right? So if I were to merge two sets that one has degree 2 and one has degree 1, it will always point to the bigger one, right? The only time that you have a decision to make is when they have equal value, right? So if they both have degree 2, you're going to need some other form of unit of comparison to see which one points to which. And usually in our homework it's always been alphabetical, right? And so if they have the same degree and we merge them, say this one was A, this one was B, then the degree will increase by 1. So this will become a 3. Right? But you only do that if you're merging two sets that have the same degree.
And then if we're using path compression?
Yeah, so the idea is say if we had C here, which pointed to B. Right? So the path compression you only use path compression when you call find on a value. So if I were to call find on C now, it will return A. Instead of having C point to B, I will immediately just point to A here. Okay. So that's all you really need to know about disjoint sets. And then TrueFalse algorithm is based on disjoint sets. Yeah, it's a very similar linear programming problem. Yeah, this one was RSA again. We did that. We didn't talk about that this semester, so don't worry about that one. We talked about that one. Let's see. So this one's talking about a min heap, and if you're adding the numbers 1 through 15. Okay. So it doesn't say how the numbers are arranged in the min heap, right? That's what the questions are going to be about. But all you know is that there's 1 through 15, and each number appears once in the min heap. Right? One thing you should know is that 1 should be the parent node no matter what happens to the tree, right? Because it's the smallest element in the heap. Right? So that's the first one. So n, I believe n is talking about the number of levels here. So how many levels are there total? Right? N levels in all. So since there's 16 elements, should be 4 levels, right? Well, technically there's only 15 elements, but there should only still be 4 levels, right? Because you can fill 16 numbers with 4 levels. What could be so this one's really interesting. What is the smallest number that could possibly be on the bottom? Right, so that would be if you were to overload one side of the tree, right? So that would look like if you had like 1, and then you'd have 2, 3, 4, right? So that would be an example there. So this would be the smallest possible number to be on the bottom. Right, and now let's see what would be the largest level? What would be the largest number on the second level? Then you would just fill this out, right? This would be 6, 7, 8. So this would be 9 in the best case. That'd be the highest, the larger value could be. Oh, sweet. Awesome. So that one is just make sure you understand what a heap is. We talked about this one. Yeah, so that one kind of wraps up this one really quickly. Though one thing I do want to note is that you should know your complexities for all these different graph algorithms we talked about in class, right? So I think the big ones that we talked about is just the topo sort, right? That you have topo sort, which was this one was E plus V, right? Or V squared. So this is adjacency, and this is a Yeah, matrix. Right, so that was the topo sort. Right, so make sure you know that one. You have Dijkstras. Right, so that's v plus e log v, right? And this log v is coming from that heap we're using, right? Because we're storing all the elements in the heap, and then we're pulling elements out one at a time from the heap, and that has a logarithmic cost. We have Bellman-Ford. This was kind of like a brute force algorithm. That would always give you like the easiest way to determine one node to another node in a graph. And that was E times V. Right. Right. So if the graph is dense here, then so if it's dense, right, this is V cubed. And then if it's sparse, then it was V squared. Right. So that's important to know. I believe we have you have DFS, right? DFS and BFS, right? So that's depth first search versus breadth first search. These were also E plus V, right? Because every node is visited, every edge and every node is visited once. Yeah.
Sorry, Bellman-Ford is E times V cubed if it's dense?
No, if it's dense, it's just V cubed, right? Because the edges can be represented as V squared in a dense graph.
Is that talking about a matrix or an adjacency list?
It doesn't matter because it's dense, right?
Okay.
Cool. So I think these are the big ones.
And it's E times V squared, you said?
Yes, for Bellman-Ford, EV squared. Yeah.
For a non-dense graph.
This could be E of V squared for every graph.
Okay.
It's just if it's dense or not, then E will be V squared
Then
versus
we have a
V.
worst case.
Yeah. Yeah. Okay. I think those are the big ones from graph theory. That's the ones I always.
Sorry, what were the last two? You said DFS and BFS? Or?
Yeah, DFS and BFS. Those are E plus V.
And what was Prims and Kruskals again?
Yeah. So Kruskals was E plus V log star V, right?
What does the star bit mean again?
Right. This is from the path compression.
Okay.
Right. So it's like a log of a log of a log of a log of a log. Right. It's a very, very fast logarithm. I believe prims. I don't have prims on the top of my head.
Is that E plus V quantity log star V?
I want to say it was E plus V. Yeah, okay. It might have been because it doesn't have the log star, right? Because that's from the path compression.
Yep.
I want to say this is log V, but it might. I'll have to I'll double check that one. I don't remember it perfectly right off the top of my head, so we can actually check the internet.
V log V plus E log V?
Yeah, I don't.
So it's O E log V?
I thought it was. I don't remember it right off.
It's making it the same as Kruskals, but the prims can be improved by using quick.
Yeah, okay. So actually, I got them slightly wrong here. This one was E times log star V, and this one was E log V. Alright, so Kruskal, they're very similar. Kruskal's a little faster if you do it correctly. Any questions on those?
It's just E log V, right?
Yeah, Prim is E log V, and Kruskal's is E log star V. So those are good. If you remember, I remember what amortized means, right? So that's finding the complexity in the average case, right? So when this was going back to like maybe the first month of school where we were consistently adding to an array list, right? So we're adding one element at a time, and like once in a while we'd have to rescale our storage, right? And that was a linear cost. But in the average case, it becomes a constant cost, right? If we pick the right rescaling factor. So we did that with mainly with array lists in this class, right? Where we found the amortized cost.
It was complexities, just finding complexity?
Yeah, right? Because like if we had 10 elements, we added 9 of them, and then the 10th one, it had linear cost, while the first 9 had constant cost. Now if we increased our array by 10 every time, then that would eventually average out to be, it'd be linear to add each element, right? But if we dynamically grow our array, so we double the size of the array each time, then on average the amortized cost would become constant. All right. So that's, I'd make sure you understand that one. I don't think you'll have this on your exam, but like in the midterm, you remember where he had like a double nested loop, and you have to see how many iterations you'll have inside the loop. I'd be comfortable with that. You know, remember Gauss's theorem? Gauss has a lot of theorems, but remember that it was like if you sum up everything like this is the same as equals 0 to n. This is like n times n plus 1 over 2, right? Make sure you remember that one. And then the sum of a geometric series, right? So that's like the sum of, if you have a, so Ri minus, so we have R here. And then I equals 0 to n, right? This is the same as a times 1 plus r to the n plus 1 all over 1 minus r. Right, so if this will only converge, right, if you have this term will only converge if you have like in an infinite series. They will only converge if r is less than 1, right? So that's like if you're adding 1 plus 1/2 plus 1/4, that will eventually converge to 2, right? But otherwise you can represent it this way. Aside from that, I don't have anything else off the top of my head, but if you know like that P versus NP, right? NP is just verifiable in polynomial time. You know what NP complete is, right? That's talking about reduction of NP problems. And then like a brief overview of how RSA works. Be really comfortable with dynamic programming. But if you have all that stuff, I think you'll be good to go. Right? If you're able to do the homework, you'll be set. So I wouldn't be too nervous about it. Okay, any questions? Awesome. Well, best of luck, guys. It's been a good semester. I'll see you on Wednesday.